Let's talk about the idea of a sampling distribution. A sampling distribution is the collection or distribution of all possible outcomes that could be found when taking a sample from the population. This idea is actually a very important idea in statistics, but before we talk about why this idea is important, we have to talk about what this idea actually means. To show you what this idea means, I have to start with an example of a very small population. Right here I have a population of 4 siblings. So you have to imagine that a certain family has 4 children, and those 4 children are a population of 4 siblings. Right here I wrote the ages of each of the siblings in that population. The youngest sibling is 23. The next sibling is 25. The next sibling is 27. And the next sibling is 29. So these are the 4 ages of the 4 siblings in the population. And right here I wrote the ages of the 4 population members in a column from person 1 down to person 4. So this is person 1, this is person 2, this is person 3, this is person 4. And imagine that we're interested in recording the ages of these 4 people, but we don't have enough time to ask all 4 population members how old they are. For some reason, we don't have enough time to contact all 4 people, so we decide to contact a sample of 2 out of the 4 population members and ask those 2 people how old they are. So if we're planning to select a sample of 2 out of the 4 people in the population and collect the ages of those 2 people, what are the possible samples that we might end up getting? We can actually find out what the possible samples of 2 people are. Well, one obvious sample of 2 people that we might get is person 1 and person 2. So let's write that down as the first possible sample. So what we're going to do is we're going to list out all of the possible samples of 2 people that we might end up selecting, and then we're going to write out the ages for each of those possible samples. So sample 1 is person 1 and person 2. Person 1 is 23 and person 2 is 25. So if we end up selecting person 1 and person 2 to be our sample of 2 people, and we record their 2 ages, then this will be the data set that we end up recording. But we don't have to select person 1 and person 2 to be our sample. We could instead select person 1 and person 3 to be our sample. So let's write that down as another possible sample. I'll move this check mark down to person 3. And the ages of person 1 and person 3 are 23 and 27. So if we select person 1 and person 3 to be our sample, and we record their ages, these will be the 2 ages that we're recording, 23 and 27, and this will be our data set. What's another possible sample of 2 people? We might end up selecting person 1 and person 4 to be our sample. So let's move this check mark down here. So the third possible sample is person 1 and person 4. And their 2 ages are 23 and 29. So if we end up selecting person 1 and person 4 to be our sample, then this will be our data set. These will be the two ages that we'll be recording. Now what we've done is we've paired person 1 with person 2. We paired person 1 with person 3, and we paired person 1 with person 4. So we paired person 1 with each person under person 1. So there's actually no more samples that involve person 1. So what we have to do now is move this first check mark down to person 2. And now let's pair person 2 with all of the people under person 2. Because remember, we paired person 1 with all of the people under person 1. So now we're going to move down to person 2 and pair person 2 with everyone under person 2. So the first one will be person 2 and person 3. That'll be sample 4. And if we select person 2 and person 3 to be our sample, then the two ages that we'll be recording are 25 and 27. We paired person 2 with person 3. Now we have to pair person 2 with person 4. And that'll be sample 5. We have to write out the ages of the two people in the sample. What about sample 6? We've already paired person 2 with everyone under person 2, so we're finished with person 2. Let's move the first check mark down here. Now we're going to pair person 3 with everyone under person 3. And the only person under person 3 is person 4. So 3 and 4 will be our last possible sample. So if we select a sample of 2 people out of the 4 people, and we record the ages of those 2 people in the sample, then we'll end up with one of these 6 possible data sets right here. We're definitely going to end up with one of these 6 data sets because these are all of the possible samples of 2 people that might be selected. There are no other possible combinations of 2 people that we could select. Now let's try to find the mean of each possible sample. Let's start by finding the mean of sample 1. To get the mean of sample 1, we have to add the 2 numbers and divide the total by 2. So we're just adding the 2 numbers and dividing by the number of numbers. There's 2 numbers, so we divide by 2. 23 plus 25 is 28. I'm sorry. 23 plus 25 is 48. 48 divided by 2 is 24. So the mean of sample 1 is 24. Remember, the symbol for a sample mean is x bar. It's an x with a bar above it. So we'll say x bar equals 24. So if we select sample 1 to be our sample, meaning if we select person 1 and person 2 to be our sample of 2 people, and we record their 2 ages, and we calculate the mean of the 2 ages that we recorded, this will end up being our sample mean. Now what if we selected person 1 and person 3 to be our sample, and we recorded their 2 ages? Then the mean of our sample will end up being something else. The mean of our sample would be the mean of 23 and the mean of 27 in that case. So let's find out what the mean of sample 2 is. We're just going to find the mean of each of the possible samples. This adds up to 50 on top. 50 divided by 2 is 25. So if we select person 1 and person 3 to be our sample, and we record their 2 ages, then our sample mean will end up being 25. Now what will our sample mean end up being if we select person 1 and person 4 to be our sample? Let's just use the calculator this time. Because they're all calculated the same way. The mean of sample 3 is 26. Now let's find the means of the other 3 samples. This one will end up being 26. Whenever you have 2 numbers that are 2 apart, the mean is just the number in between them. That's a shortcut you can remember. Actually, whenever you have 2 numbers like this, the mean is just the number halfway between them. So the mean will end up being 27 here. And the mean will end up being 28 right here. So now we know that if we select a sample of 2 people, these are the 6 possible samples that we'll be selecting from. And we can see that each possible sample has a sample mean. If we list out the means of all of the possible samples, then we have something called the sampling distribution. So I'm going to write sample 1, sample 2, and so on, all the way down to sample 6. And we're just going to write out the mean of each possible sample. Sample 1 had a mean of 24. Sample 2 was 25. Sample 3 had a mean of 26. I'm just writing out the mean of each of the 6 samples. These are all of the X bars that we have over here. And these 6 numbers inside of here make up the sampling distribution. Because remember, the sampling distribution is the collection of all possible outcomes that could be found when you take a sample from a population. In this case, when you take a sample of 2 people from this population of 4 people, and you calculate the mean of your sample, these are the 6 possible outcomes that you might find. In other words, when you record the ages of 2 people and you calculate the mean of the sample of 2 people, you're definitely going to end up with one of these 6 sample means that are inside of here. And we could also write n equals 2, meaning we're talking about all possible outcomes that might be found when using a sample size of 2. Now what if instead of selecting a sample of 2 people, we were selecting a sample of 3 people? Then we would have a different set of possible outcomes. So let's think about how we could write out all of the possible samples of 3 people. In order to make room for that, let's move all of this up here. Let's clear off some of this to give us some more space. Well, one obvious possible sample of 3 people is person 1, person 2, and person 3. So let's write that down as sample 1. Let's also write the ages of all of the people in the sample. Now what's another possible sample of 2 people? I'm sorry, what's another possible sample of 3 people? What we can do is, each time we write out a sample of 3 people, we just leave out one person. So I'll show you what I mean. When we did sample 1, we left out person 4 because our sample was just person 1 to person 3. Now let's move the red check mark up to person 3. So this time we're going to be leaving out person 3 instead of person 4, which means the next possible sample will be person 1, person 2, and person 4. Their ages are 23, 25, and 29. Now let's move the red check mark up to person 2. The next possible sample of 3 people will be person 1, person 3, and person 4. Everyone except person 2. So each time we're just leaving out a certain person. Oh, I'm sorry, I made a mistake over here. So I need to fix this. This is supposed to be person 1, person 2, and person 4. Leaving out person 3. So we left out person 4, then we left out person 3, then we left out person 2, and now we're going to leave out person 1. And that'll be our last possible sample of 3 people. So 1, 2, 3, 1, 2, 4, 1, 3, 4, and this one will be 2, 3, 4. So if we're selecting a sample of 3 people out of this population, then these are the possible samples we're drawing from. We'll definitely get one of these 4 samples if we're selecting 3 people, because these are the only possible samples of 3 people. And we can see that each of the possible samples has its own data set. For example, if we select sample 1, if we select person 1, person 2, and person 3, this will end up being our data set. And if we select person 1, person 2, and person 4, this will end up being our data set. And each of these different data sets has its own mean, just like we did up here. So let's start by finding the mean of sample 1. If we want to find the mean of sample 1, we add the 3 numbers, and then we divide by 3, because to get a mean, you just add the numbers, and then you divide by the number of numbers. So it'll be 23 plus 25 plus 27 over 3. Comes out to 75 over 3, because these numbers add up to 75. 75 over 3 is 25. You get 25 when you divide 75 by 3. Remember, the symbol for a sample mean is x bar, so we'll say x bar equals 25. Now let's find the mean of each of the other samples. What's the mean of sample 2? This adds to 48. 23 plus 25 is 48. 48 plus 29 is 77. So it's 77 over 3. "77 divided by 3 is 25.67 if we round to 2 places. So we added the 3 numbers, and then we divided the total by 3, and we got 25.67. Now let's find the mean of sample 3. We add the 3 numbers, and we divide the total by 3. 23 plus 27 plus 29 equals 79. That's the total, and 79 divided by 3 is 26.33. That's the mean of sample 3. What about the mean of sample 4? 25 plus 27 plus 29 gives us a total of 81. 81 divided by 3 is 27. So now we found the mean of sample 1, the mean of sample 2, the mean of sample 3, and the mean of sample 4. These 4 sample means make up another sampling distribution. It's the sampling distribution of the sample size of 3. So let's write out this sampling distribution. And instead of putting n equals 2, we'll put n equals 3, because this is the collection of all possible outcomes that might be found when using a sample size of 3. If we take a sample of 3 people and record the ages of the 3 people and then calculate the mean of the sample, we'll end up with one of these 4 numbers. So these 4 numbers are the collection of possible outcomes that could be found when using a sample of 3 people. So let's write out those possible outcomes. The mean of sample 1 is 25. The mean of sample 2 is 25.67. The mean of sample 3 is 26.33. And the mean of sample 4 is 27. Now what I'd like to do next is make a histogram for the population and for both of the sampling distributions. And I'll make the histogram a little bit differently than I've made it before. Instead of using a y-axis, I'll just stack boxes on a number line. I'll show you what I mean. Before I do that, I'll probably label what these are so we can keep track of the work we've done. These were the samples of 2 people. These were the samples of 3 people. So let's start with the population and make a histogram. The population, the ages of the people in the population go from 23 to 29. So maybe we could start at 20. Maybe we'll start at 20 and go up to 29 if we have enough room. Okay, so person 1 is 23, so let's make a box right there. This is person 1. Person 2 is 25 years old, so let's put a box right there. Person 3 is 27. We'll put a box there. And then person 4 is 29. So we have one more box here. We didn't really have to put these numbers down here because there's no people down here. The reason why I included these three numbers is so that I can use the same number line for all three histograms. I want to use the same number line for all three of them so we can actually compare the shapes of the different histograms. So now let's do sampling distribution n equals 2. I'm going to erase these boxes and replace them with the boxes that show the numbers in this sampling distribution right here. So now each box isn't a person. Each box will be a sample. So in this list right here of n equals 2, sample 1 was 24, had a mean of 24. So that sample goes there. Sample 2 had a mean of 25, so we put a box there. Sample 3 had a mean of 26, which is right here. And also, sample 4 also had a mean of 26. So what we'll do is we'll stack a second box above 26. So these are sample 3 and sample 4. Sample 5 had a mean of 27. And sample 6 had a mean of 28. So we'll put one more box right there. So now we've created a histogram for the population and a histogram for the population. Now let's make a histogram for the sampling distribution for the sample size of 3. So I'll just copy and paste this number line again. And I'll erase the boxes. And I'll put boxes for all 4 of these samples. So in this list right here, sample 1 had a mean of 25, which is right here. Sample 2 had a mean of 25.67. So we're actually going to have to make some smaller boxes to fit all of these on here because 25.67 is between 25 and 26. It's about right there. And 26.33 is a little bit above 26. So we'll put the box for sample 3 right here. And then we want to put one more box for sample 4. Sample 4 had a mean of 27, so that box goes above 27. So now we've made a box for each of these 4 numbers. And now we have a histogram for the population the histogram for this sampling distribution and the histogram for this sampling distribution. I'm going to discuss these histograms a little bit more, but first I'm going to make one other point. I'm going to talk about the mean of the population and the mean of the sampling distribution. When we calculate the mean of the population and we calculate the mean of the sampling distribution, we'll see that they both come out to the same number. So let's find the mean of the population. The mean of the population is the total of the 4 numbers in the population divided by 4. We just add the numbers and then divide by the number of numbers. Let's add the numbers on top. They equal 104. So it's 104 over 4. Which is 26. So the population mean is 26. Remember the symbol for population mean is the Greek letter mu. So right here I can say mu equals 26. That's the population mean. Now let's find the mean of this sampling distribution. In order to find the mean of these numbers, we need to add the 6 numbers and divide the total by 6. So it'll be 24 plus 25. The total of the 6 numbers in here is 156. When we divide that by 6, we get 26. So the mean of these 6 numbers in here is 26, which is the same as the mean of the population. And the symbol for the mean of a sampling distribution is mu with a little x bar at the end. So it's actually a subscript of an x bar. And I said that the mean of the population equals the mean of the sampling distribution. That's actually true no matter what sample size you're dealing with. So, and then if you calculate the mean of these 4 numbers, then it'll turn out that the mean of these 4 numbers is also the same as the population mean. So let's try to show that the mean of this other sampling distribution is also 26. You have to add the 4 numbers and then divide the total by 4. So the total is 104 divided by 4 is 26. So the mean of the population is the same as the mean of the sampling distribution, regardless of whether you're dealing with a sample size of 2 or a sample size of 3. no matter what the sample size is, the mean of the sampling distribution will be the same as the mean of the population. Is the mean of the population and the mean of all of the sampling distributions come out to the same number. They all come out to 26. So let's label the population. Let's label the population mean under each of these histograms. We can see that the population mean of 26 is at the center of each of these histograms. Remember, the symbol for population mean is mu. Now I wanted to talk about the shapes of these different histograms. We can see that the population is flat, and we can also see that it's the most spread out. So compared to these other two histograms, the population has the most spread between the values. We can see that in the sampling distribution for the sample size of 2, the boxes are getting less spread out. They're moving in closer together because the 23 moved up to 24, because now the lowest box is 24, and the 29 box moved up to 28. And we also have 2 boxes right at the center. So when we go from this histogram to this histogram, the boxes, meaning the values, are getting less spread out. And when we go down to this last histogram, we can see that the values shown by these boxes here are even less spread out. They're moving in even closer together because now the 24 moved up to 25 right here, and the 28 moved up to 27. So now all of the boxes are in this narrow area between 25 and 27. So overall, the population has the most spread. The samples of 2 people have less spread, and the samples of 3 people have the lowest spread of all. So as we go from here to here to here, we're getting less and less spread. The reason why we're getting less spread is because each of the, as we go from here down to here, each box is based on a larger number of people. In this case, up here in the population, each box is only 1 person. In this histogram, each box is actually 2 people. It's actually a mean of 2 people. And down here, each box is actually a mean of 3 people. So as we go from values based on 1 person to values based on 2 people to values based on 3 people, we're getting less and less spread. So what we're saying is this set of numbers has the most spread, this set of numbers has less spread, and this set of numbers has even less spread. So what that should mean is that this set of numbers would have the highest standard deviation, this set of numbers would have a lower standard deviation, and this set of numbers would have the lowest standard deviation. And we can see if that's actually true. So if we wanted to calculate the standard deviation of each of these numbers, we would have to, we'd have to go through the steps of subtracting each number by the mean of 26 and getting the answers, which are the deviations, and then squaring each of the deviations, and then getting the mean of the squared deviations, which is the variance, and then finding the square root of the variance. We can actually just go through those steps in Excel to save us some work. So let's type in 23, 25, 27, and 29. And then let's find the mean of these numbers. We type in equals average. We put a parentheses right there. We highlight the numbers, and then we can close it like this. And we get the average of 26. What we can do now is we can type in an equal sign right here, highlight this box, put a subtraction sign, and then highlight the mean of 26, and it'll put it in there. A11 just stands for cell number A11, and then press enter, and it subtracts it. So this is 23 minus 26 is negative 3. We can then put the mouse right here at this corner and drag it down, and it does it for all 4 of them. Oh wait, in order to make this work, you have to go here and then type in a $sign before the A, and then a $sign before the 11, and then press enter. You have to do that for it to keep subtracting by 26 each time. So now drag it down. Now it subtracts each number by 26. So this was our population. These were the deviations. Squared deviations. What we can do now is type in the equal sign, highlight this, and then press shift and then number 6 at the same time. Shift 6 puts in this symbol right here, and then type in a 2 and press enter. And this means V6 squared, which is really just negative 3 squared. And it squares this number. Minus 3 times minus 3 is 9. Now we can click here and drag down, and it'll square all of these numbers. Remember that the variance is the mean of the squared deviations. So we just need to type in equals average, and we can get the mean of the squared deviations. The variance is 5. And then we can type in the equal sign right here. Now we type in equals SQRT for square root, put a parentheses right there, highlight this number, and then close the parentheses, and press enter. This is the standard deviation of the population. And when we calculated this number up here, the variance, what we did was we used average, so it added these 5 numbers and divided the total by 5. So we didn't have to use n minus 1 this time because n minus 1 is only for a sample standard deviation. If it's the entire population, you just add these numbers and divide by n. So, but we just added the 5 numbers here and divided by 5 because um, n is 5. So now we know the standard deviation of the population. Oh, I'm sorry, that's not the right symbol. The symbol for the population standard deviation is this symbol right here. It's the sigma, and we saw in Excel that it equals 23 point, 2.236, which rounds to 2.24. Now let's find the standard deviation of these numbers right here in this sampling distribution. We have 24, 25, 2 26s, 27, and 28. We need to get the mean of all of these numbers in here. So we type in equals average. We highlight the numbers, and then we close the parentheses and press enter. We get the average, which is 26. Then we type in equals. Highlight this. Remember, we have to put in the dollar signs. There has to be a dollar sign right here and right here. Then we can press enter. Oh, I'm sorry. I didn't do this right. What we do is we hit enter. We highlight this first, E6. Then we put a minus sign in here for subtraction. Then we highlight this. So we're subtracting this by this. And now we put in the dollar signs for E13. Press enter. Now if we drag it down, it subtracts all of these by the mean of 26 to get the deviations. If we type in equals and then highlight this and put this in here again, it squares -2. And if we drag it down, it'll square all of the other numbers. It squares all of these deviations. And now we can find our variance, which is, variance will be the total of these numbers divided by the number of numbers. So the total of the squared deviations divided by the number of squared deviations. So there's 1, 2, 3, 4, 5, 6 of them. So we'll divide by 6. When we're calculating the standard deviation of a sampling distribution, like this one right here, we actually won't use n-1. n-1 is used when you have data from a sample, meaning, for example, like data from a sample of 2 people. So if we wanted to calculate the standard deviation of these 2 numbers in this sample, we would use n-1. But if it's the standard deviation of a sampling distribution, like this right here, it's actually not n-1, it's just n, because every possible sample is included in here and none are left out. So you can think of this as being a population of possible samples. And since it's a population of possible samples, without any being left out, we would use the population formula, which is n and not n-1. So we can just type in equals average, highlight these squared deviations, and press enter. It'll add these and divide the total by 6, and we get 1.67. So the standard deviation of these numbers in here is 1.67. Since it's the standard deviation of a sampling distribution, we use this symbol, which is sigma with a little x bar. And notice how this standard deviation came out to a bigger number than this standard deviation. So I said that when you go from the population to the sampling distribution of n equals 2, there's less spread. And that's why our standard deviation was higher here and was lower here. Because when a set of numbers has less spread, the standard deviation is lower. And I said that this set of numbers down here had the lowest amount of spread, so its standard deviation should be even lower than this number. So let's find out what the standard deviation is for that other sampling distribution for samples of 3. The numbers were 25, 25.67, 26.33, and 27. We're just going to do all of those same steps over again. I'm just getting the average of these samples. Now I subtract all of these by this mean of 26. So we found the mean of the 4 numbers, and now we're just subtracting each of those numbers by the mean. Now we can square each of these deviations. So these are the square deviations. And then we can get the variance, which is just the mean of these square deviations. So we type in equals average. And then we can get the square root, which is equals SQRT. So the standard deviation comes out to 0.744 for this set of numbers right here, for the sampling distribution with n equals 3. So we'll just round that off to 0.74, and we'll use this symbol again, because it's the standard deviation of a sampling distribution. And it came out to a lower standard deviation than the standard deviation we got here, and that's what I expected it to be. Because I said, as we go from here to here to here, we're getting less and less spread, which means that the standard deviation is the highest for the entire population. It's lower for this sampling distribution, and it's lowest for this sampling distribution. So right here, the standard deviation is 2.24. Here it's 1.67, and here it's 0.74. So as we get less and less spread, we get lower and lower standard deviations. And there's actually a special name for the standard deviation of a sampling distribution. It's called a standard error. So whenever you have a standard deviation, and it's the standard deviation of a sampling distribution, the term for it is a standard error. So we would call this a standard error, and we would call this a standard error, even though they're really just standard deviations. And this one over here would just be called the population standard deviation. So the standard deviation of the individual people in the population is the population standard deviation. The standard deviation of the means of all of the possible samples is called a standard error. So whenever you take the means of all of the possible samples, which we have here, and you plug them into a standard deviation formula, your answer is called the standard error, even though it's really just a standard deviation. Next, we'll talk about the idea of a z-score, and we'll also talk about the idea of a margin of error and a confidence interval. First, I can add one more definition in here. We said that a standard error is the standard deviation of a sampling distribution. So I'll put that definition right here. Actually, before I move on to the new topics, there was a couple other things I wanted to talk about. First, I wanted to say that the standard error of this sampling distribution will always be larger than the standard error of this sampling distribution, because whenever you take a population and you create a sampling distribution with a smaller sample size, and you create a sampling distribution with a larger sample size, the sampling distribution with the smaller sample size will always have the bigger standard error, and the sampling distribution with the bigger sample size will always have the smaller standard error. So smaller sample size means larger standard error, larger sample size means smaller standard error. It's always that way, because whenever you go from the smaller sample size to the bigger sample size, then the possible samples have less spread. So the possible samples with a smaller sample size of 2 have more spread, and the possible samples with a larger sample size of 3 have less spread. So that's what always happens when your possible samples have a smaller sample size. The possible samples have more spread. When your possible samples have a larger sample size, then the possible samples have less spread. Which is why, like I said, a smaller sample size means a bigger standard error, and a larger sample size means a smaller standard error, because the standard error is just the standard deviation of the possible samples, which means that if the possible samples have less spread, then the standard error is smaller. Now we can move on to our next topic, and I'll start a new slide for that topic. Here we have a population of 5 people. I already calculated the population mean and the population standard deviation. I'm going to use this example here to explain some different concepts such as the margin of error and a confidence interval and z-scores. You can see that I've already created all of the possible samples of 3 people. I've listed them all out here. There's 10 possible samples of 3 people. I've already calculated the mean of each possible sample. The first concept that I want to go over is the z-score. Each of these possible samples will have its own z-score. And what the z-score does is it shows how far each sample is, how far each sample mean is from the population mean of 24. And I think you'll see that once I show you how to use the formula. So let me write out the formula right here. The z-score of a sample mean is z equals x bar, which is the sample mean, minus the population mean, over the population standard deviation, which is the sigma, over the square root of n, which is the sample size. Let's try to calculate the z-score of sample 1. We know that the sample mean is 22, so x bar is 22. We know that mu, the population mean, is 24, because I already calculated the population mean and it came out to 24. We know that sigma, right here, which is the population standard deviation, is 2.83 because I already calculated that. And then we put this over the square root of n. N is the sample size. So in this case, the sample size is 3 because the sample has 3 people. N is just the number of people in the sample. So it's over the square root of 3. This will give us a z-score. To get the population mean and the population standard deviation, I entered these 5 numbers into Excel, and Excel was able to calculate the mean and the standard deviation of the 5 numbers in here. And the mean and standard deviation of the 5 numbers in here are the population mean and population standard deviation. So let's try to calculate this z-score. What we can do first is work on the bottom of the fraction. So let's find out what the square root of 3 equals. It's easiest to do the square root first. So it's 1.73. So we can change this to 1.73. So it's 2.83 over 1.73. Now let's divide on the bottom. Let's divide 2.83 by 1.73. We get 1.635. We could round that up to 1.64. Now we subtract on the top of the fraction 22 minus 24, which will end up being -2. So the z-score will be whatever -2 divided by 1.64 equals. On my calculator, I can divide 2 by 1.64, and I get about 1.219, which rounds to 1.22. And remember that we divided -2 by 1.64, which means that you're actually dividing a negative number by a positive number, which means that the answer will be negative. So it's actually -1.219, which rounds to -1.219, which is about -1.22. So our z-score for sample 1 is -1.22. We could do the same thing for sample 2. Sample 2 will also have a z-score. Every possible sample will have its own z-score. So there are 10 possible samples of 3 people that could come from this population of 5 people, and each of the 10 possible samples will have its own z-score. Some samples might end up having the same z-score, but what I mean is we can calculate the z-score of each individual sample, and we'll end up getting an answer for each possible sample. So this one would be 2.67 minus 24, the population mean. It's the sample mean, x bar, the mean of sample 2, minus the population mean of 24. And we've already done this work down here. And this down here will actually be the bottom of every z-score. So every z-score that we calculate going across has 2.83 over the square root of 3 on the bottom of the fraction. So we've pretty much done all of the work already. Because we know that the square root of 3 is 1.73. We know that this is 1.73. We know that 2.83 divided by 1.73 right here equals 1.64. So now all we have to do is just subtract the sample mean by the population mean and divide by 1.64. So it's negative 1.33 on the top, over 1.64, Let's see what that equals. We'll divide negative 1.33 by 1.64, and we get negative 0.81. That's what it rounds to. Now let's actually skip to this one out here and calculate this z-score. This one will be 26 minus 24 over this right here, the population standard deviation over the square root of the sample size. We know that the square root of 3 is 1.73. So I'll change this to 1.73. And I know that the bottom right here equals 1.64 when you divide these after you divide these two numbers. So 26 minus 24 is 2. So it'll be 2 over 1.64. Notice back here we were dividing negative 2 by 1.64, and we got negative 1.22. Now we're dividing positive 2 by 1.64, which means we'll get the positive version of this answer, because a positive divided by a positive is a positive. So when you divide 2 by 1.64, you'll get 1.22. Let's actually try sample 9 next. I'm going to copy and paste so I don't have to write everything over again. So the mean of sample 9 is 25.33. So I'll change this to 25.33. It's 25.33 minus 24. So what does this equal when you subtract? We get 1.33. Actually, I have to change all of this first. 25.33 minus 24. I said that the top equals 1.33. So it'll just be whatever 1.33 divided by 1.64 equals. Before we had negative 1.33 over 1.64. Here we have positive 1.33 over 1.64. So when we divide, we'll just get the positive version of this answer. It'll just be positive 0.81. So if I divided these two numbers on my calculator, I would get 0.81. This divided by this is 0.81. Notice right here how the population mean is 24, and sample 5 has a mean of 24. Whenever the sample mean equals the population mean, z is 0. So this one will have to be 0, because the top of the fraction will be 24 minus 24, and we'll get a 0 on the top of the fraction, which just means that the entire z-score will equal 0. What about these ones right here? Instead of going through all the work again, I'll just take a shortcut, because if I subtract 23.33 minus the population mean of 24, and I divide by 1.64, which is the bottom of the fraction, I get the z-score. So this sample 4 has a z-score of negative 0.41, rounded. And this one right here is actually going to be positive 0.41. If I did the math, that's what it would come out to. So let's notice a few things. If the sample mean equals the population mean of 24, z is 0. So z is 0 whenever the sample mean equals the population mean. When the sample mean is further away from the population mean, the z-score gets further from 0. So as a sample mean gets further and further below the population mean, the z-score gets further and further below 0. So notice how z is getting further below 0 as we move out toward the left. When the sample mean gets further above the population mean, toward the right out here, the z-score gets further and further above 0. So notice how as the sample mean is getting further and further above the population mean of 24, the z-score is getting further and further above 0. So the z-score goes from this to this down here to this up here. Remember, these were the z-scores that we calculated. So when the sample mean equals the population mean, z is 0. When the sample mean is below the population mean, z is a negative number. When the sample mean is above the population mean, the z-score is a positive number. And when the sample mean is further away from the population mean, then the z-score gets further from 0. Like I said, as the sample mean gets further below the population mean, z gets further below 0. As the sample mean gets further above the population mean, z gets further above 0. So the z-score is a way of showing how extreme the sample is. And what I mean by extreme is how far the sample mean is from the population mean. These samples down here, toward the left end, are getting more and more extreme because their sample mean is further and further away from the population mean. Going in this direction, we're also getting samples that are more and more extreme because the sample mean is getting further and further away from the population mean. So as we go toward the left end, and the samples are getting more extreme this way, z is getting further below 0. As we get to samples that are more extreme in this direction, z gets further above 0. So pretty much a sample that's further from 0 is more extreme. Now that we've covered the idea of a z-score, let's talk about the idea of the margin of error. I'm going to clear all of this work here and just put the z-scores across up here so that I have more room to work with. So now I've listed out the z-score of each sample going across here. I'll also create a histogram down here of all the possible samples. So down here we have sampling distribution shown as a histogram. Each box is one of the 10 possible samples, and each box is stacked above the sample mean. So this is a sample with a mean of 22. These are the two samples with a mean of 24, and this is the sample with a mean of 26. Let's talk about the idea of the margin of error. So before we can talk about the margin of error, we need to think about a certain percentage that we want to use. So let's try to figure out which two samples have 80% of the samples between them. So if we look at this sample right here, which is sample 2 with a mean of 22.67, and we look at this other sample up here, which is sample 9, which has a mean of 25.33, we'll notice that 80% of the possible samples fall between those two samples. So see, we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 out of the 10 samples are between sample 2 and sample 9, because only 2 out of the 10 samples are beyond these two samples. So right here I'll say that 80% of the possible samples are between sample 2 and sample 9. Now we know that the population mean is 24. So the population mean is in the center of the sampling distribution. We actually have two samples that have a mean of 24. But let's think about these two endpoints of the middle 80%, which are the sample 2 and sample 9. And let's think about how far their two sample means are from the population mean of 24. We can find out how far they are by subtracting. So let's subtract 25.33, which is the mean of sample 9, by the population mean of 24. It comes out to 1.33, which means that the distance from this sample mean right here of 25.33 to the population mean of 24 right here is a distance of 1.33. Now let's look at this boundary right here. Let's look at the mean of sample 2, which is 22.67, and let's think about how far that sample mean is from the population mean of 24. We can find out by subtracting. $22.67 minus 24. And we actually get negative 1.33. So it's really the same distance, meaning this sample mean right here is 1.33 away from the population mean of 24. The only reason it came out to a negative number is because this is lower than this. So we can see that the distance from these two boundary points of the middle 80% to the population mean at the center is a distance of 1.33, which means we would say that the 80% margin of error equals 1.33. So the 80% margin of error is just the distance from the boundary points of the middle 80% to the population mean at the center. Now, what if we wanted to find the 60% margin of error? Well, before we can find the 60% margin of error, we have to start by thinking about what are the middle 60% of the possible samples? Well, the middle 60% would be the middle 6, because 6 out of 10 is 60%. And it looks like the middle 6 would be these 6 samples in here, which are samples 3, 4, 5, 6, 7, and 8. So let's mark off sample 3 as a boundary. Let's also mark off sample 8 as a boundary. These are the boundaries of the middle 60%. Because, well, these two samples are the lowest two, and these two samples are the highest two. So those 4 samples don't fall in the middle 60%. The middle 60% would be the 6 samples going from sample 3 to sample 8. So this is the middle 60%. And the 60% margin of error would be the distance from the two boundary points of the middle 60%, which are sample 3 and sample 8, to the population mean at the center, which is the population mean of 24. So let's find out how far that distance is. So sample 3, which is at the lower boundary point of the middle 60%, has a sample mean of 23.33. So what's 23.33 minus the population mean of 24? It's negative 0.67. So that's this distance from this sample to the population mean. I mean, from this sample mean to the population mean. It's negative point. Well, the distance is just 0.67. The distance won't be a negative number. And if we wanted to find the distance from sample 8, which is at the upper boundary of the middle 60%, to the population mean of 24, we could subtract this sample mean at this boundary, which is 24.67, by the population mean of 24. And we would get 0.67, which is the same distance. So the distance from the sample mean at this boundary, at sample 8, to the middle, which is the population mean of 24, is 0.67. So 0.67 is the distance from the two boundary points of the middle 60% to the population mean of 24. So we would say that the 60% margin of error is 0.67. So I said that the 80% margin of error was the distance from the two boundary points of the middle 80% to the population mean of 24, and that turned out to be 1.33. The 60% margin of error is the distance from the two boundary points of the middle 60% to the population mean of 24, and that turned out to be 0.67. So we know what the margin of error is. Now let's think about what a confidence interval is. If you take the mean of a sample and you add and subtract the margin of error, you get two numbers, and those two numbers give you something called the confidence interval. So let's try that for some of these samples. I'll move this down so we have more space. Let's start with sample 1. The mean of sample 1 is 22. If we add and subtract the 80% margin of error, which is 1.33, we'll have something called an 80% confidence interval. So let's try to do that. Let's take 22 and add and subtract the 80% margin of error. When we subtract 22 by 1.33, we get 20.67. And when we add 22 plus 1.33, we get 23.33. And the confidence interval is actually the distance or the interval between these two numbers. So we would say that the 80% confidence interval goes from 20.63 to 23.33. Let's try to do this with one sample that's in the lower part, below the middle 80%. Let's do it with a sample that's in the middle 80%, and let's do it with a sample that's above the middle 80%. And I want to do that just to make a point. So sample 3 is in the middle 80% because the middle 80% goes from sample 2 to sample 9. Anything between sample 2 and sample 9 is in the middle 80%. So I said we'll do it with sample 3. We'll take the sample mean of sample 3, which is 23.33. We'll add and subtract the 80% margin of error, which was 1.33. And we get 22 for the lower number, and for the upper number we get 24.66. So we can see that each of the 10 samples has its own 80% confidence interval. Whenever you take a sample mean and add and subtract the 80% margin of error, you get an 80% confidence interval. So it's possible to create an 80% confidence interval with all 10 of the possible samples. So this is the 80% confidence interval for sample 3. It goes from 22 to 24.67. Now let's do it with a sample that's above the middle 80%. The only sample that's above the middle 80% is sample 10, because the middle 80% goes from sample 2 to sample 9. So let's do it with sample 10. Let's add and subtract from 26. If we subtract 26 by 1.33, we get 24.67. And if we add 26 plus 1.33, we get 27.33. And notice when we did this with a sample that was below the middle 80%, meaning below sample 2, we got a confidence interval that did not include the population mean of 24. So the population mean isn't inside of this confidence interval. It's above the confidence interval out here. When we took a sample from the middle 80%, meaning a sample between sample 2 and sample 9, and we created a confidence interval, the population mean did end up falling inside the confidence interval because 24 is between these two numbers in the confidence interval. So if we did this for all samples between sample 2 and sample 9, meaning if we created an 80% confidence interval for all samples that are in the middle 80%, all of them would include the population mean inside the confidence interval. Well, let's see what happened when we used the sample that was above the middle 80%. If you take a sample that's above the middle 80% and you create an 80% confidence interval, the population mean won't fall inside the confidence interval. It'll fall below the confidence interval down here. See how 24 is below 24.67? Let's now look at what happens if we create an 80% confidence interval for sample 2 and sample 9, which are at the boundary points of the middle 80%. If we did it for sample 2, it would end up being 21.34 to 24. I'm pretty sure that's correct. And if we did it with sample 9, it would end up being 24 to 26.66. So notice how when we create the 80% confidence interval with the samples at the boundary points of the middle 80%, the confidence interval barely reaches the population mean. So we can visualize what's happening here with this graph down here. If you use one of these two samples that are at the boundary points of the middle 80%, and you create a confidence interval around the sample mean, the margin of error that you're adding and subtracting is barely long enough to reach the population mean. This one went to 21.34, which is about right here. When we do it with this sample right here, which was sample 9, the margin of error is barely long enough to reach the population mean going in this direction, 24. When you use one of the middle, when you use one of the outer samples that are outside of the middle 80%, the margin of error isn't long enough to reach the population mean. It falls short of the population mean. So it's like when a person's arm isn't long enough to reach something. You can see if we add and subtract the margin of error to this sample mean of 22, which I did right here. This is the 22 at the center. It falls short of the population mean of 24. Same thing happens if I use 26. When I add and subtract the margin of error only goes down to 24.67, meaning it doesn't reach the population mean of 24. It comes short. So if I use one of the samples that are outside of the middle 80%, the margin of error won't reach the population mean. But if I use one of the samples that are inside of the middle 80%, meaning if I use one of these samples inside of here, then, meaning not one of the boundary points, but actually one of the samples in between the boundary points, then the margin of error that you're adding and subtracting actually crosses over the population mean and goes past it, which means that the population mean actually falls inside of the confidence interval. Notice how when I use the sample mean of 23 right here, which one of the samples would that be? Well, it's actually a sample mean of 23.33, which is either sample 3 or sample 4. When I create the confidence interval with one of those samples, when you add the margin of error, it goes up to 24.67. So this is going up to 24.67. It's crossing over, it's going past the population mean. And in this direction, it's going down to 22, because when you subtract 23.33 by 1.33, it goes down to 22. So if it's not one of the boundary points, and it's actually between the boundary points inside the middle area, then the margin of error will cross over and go past the population mean. Now let's see what happens when we create 60% confidence intervals. If we want to create a 60% confidence interval, we add and subtract the 60% margin of error. Now let's try to do this with one of the samples that's below the middle 60%, one of the samples in the middle 60%, and one of the samples above the middle 60%. You know what the boundary points of the middle 60% are sample 3 and sample 8. So we can choose either sample 1 or sample 2 because they're both below the middle 60%. I guess we could do it with sample 2. So to get this confidence interval, we have to add and subtract the 60% margin of error. So what's 22.67 plus 0.67? When you add, it comes out to 23.34. When you subtract, it comes out to, let's see, 22. So our 60% confidence interval for sample 2 is 22 to 23.34. Notice how it doesn't reach the population mean of 24. The reason why is because it's below the middle 60%. If you create a 60% confidence interval with a sample that's below the middle 60%, the confidence interval won't reach the population mean. Let's do it with one of the samples inside the middle 60%, maybe sample 6. If we add and subtract 0.67 to 24.67, we get, well, 24 minus 0.67 is 24. 24.67 plus 0.67 is 25.34. So this, the confidence interval, the 60% confidence interval for sample 6 does include the population mean. Now let's try it for one of the samples that's above the middle 60%, which would be sample 9 or sample 10. When we do it with one of these, it's not going to include the population mean because it's outside of the 60% middle area. We could do it with sample 10. Remember, we could do it with sample 9 or sample 10 this time because those are both above the middle 60%. This one would be, well, 26 minus 0.67 would be 25.33. 26 plus 0.67 would be 26.67. So we've created another 60% confidence interval. And since we did it with a sample above the middle 60%, it didn't include the population mean. So right here, we'll say that these are the 80% confidence intervals. These in this row are the 60% confidence intervals. I wanted to point out that this confidence interval right here is one of the 60% confidence intervals. I wanted to point that out because it might be a little bit difficult to see which row it's in. This is actually in the bottom row with the other 60% confidence intervals. One thing we should notice is that the 80% confidence intervals are wider than the 60% confidence intervals. For example, right here, this 80% confidence interval for sample 2 goes from 21.34 up to 24. But the 60% confidence interval for sample 2 goes from 22 to 23.34, which is a narrower interval of numbers. The reason why the 80% confidence interval is wider and the 60% confidence interval is narrower is because when we created the 80% confidence intervals, we added and subtracted the 80% margin of error, 1.33. And when we created each of the 60% confidence intervals, we added and subtracted the 60% margin of error, which was 0.67. So when we added and subtracted the 80% margin of error, we were adding and subtracting a larger number. When we were creating each of the 60% confidence intervals, we were adding and subtracting a smaller number. So since the 80% margin of error is larger than the 60% margin of error, each of the 80% confidence intervals is wider than each of the 60% confidence intervals. So a confidence interval with a higher percentage will always be wider. So if we had created 90% confidence intervals, those would have been even wider than the 80% confidence intervals. The reason why they would have been wider is because the margin of error would have been even larger. We would have been adding and subtracting the 90% margin of error, which would be an even bigger number than 1.33. So as the percentage goes up, the margin of error gets larger and the confidence interval gets wider because you're adding and subtracting a larger margin of error. The next thing I want to do is show you a formula that can be used to take a z-score and actually use the z-score to calculate the margin of error. So how can we use a z-score to calculate the 80% margin of error? Well, what we can actually do is we can use the z-score of the sample that's at the upper boundary of the middle 80%, which is this z-score right here, and actually use this z-score to get the margin of error of 1.33. So I'll say margin of error formula is it's actually this right here, which is z with this is an alpha. It's actually a Greek letter divided by 2. times the population standard deviation, which is a sigma over the square root of n. What this z-score is called is a confidence coefficient. And it's called a confidence coefficient because it's not just any z-score, it's actually a certain z-score. It's the z-score of the sample at the upper boundary of the middle area. So if we're calculating the 80% margin of error, our confidence coefficient would be the z-score of the sample that's at the upper boundary of the middle 80%, which is this z-score right here. So this is our confidence coefficient. It's 0.81. You multiply the confidence coefficient by the population standard deviation, which we have over here, 2.83, and that over the square root of n. In this case, n is the sample size, and it's the sample size of all of the possible samples. All of these possible samples have a sample size of 3, which means n is 3 in this example. Now, in order for us to do this work, I have to move this histogram. Let's start on the inside and divide 2.83 by the square root of 3. We know that the square root of 3 is, well, we did the work before. It's 1.732. So what we're going to be doing is we're going to be dividing 2.83 by 1.732 because that's the square root of 3. So let's do that. 2.83 divided by 1.732. I think that was correct. Let me double check it. The square root of 3 was 1.732. So it's 2.83 divided by 1.732, which equals about 1.63. Times the confidence coefficient of 0.81. Multiply these two numbers together as our last step. And we get 1.323, which is about 1.33. You must have rounded somewhere, so that it caused it to be off a little bit, but it should come out to 1.33, which is the which we already know is the 80% margin of error. So we used a formula to calculate the 80% margin of error, which is something that we actually already had. We knew what it was by looking at the samples and by finding the distance from the population mean to the endpoints. But this time what we did is we actually just used a formula to get the same number. It's just what we did here was just another way of getting our same answer of 1.33. So this is the 80% margin of error. What if we wanted to use a formula to get the 60% margin of error, which we already know is 0.67? In this case, we would use a different confidence coefficient, because if we want to calculate the 60% margin of error, our confidence coefficient is the z-score at the upper boundary of the middle 60%. which is, in this case, the z-score of sample 8, which is the z-score of 0.41. So to get the 60% margin of error, we just have to replace our confidence coefficient. This will also be replaced. Now we're multiplying these two numbers. And we get 0.6683, which rounds to 0.67, which is our 60% margin of error. We already knew that that was what it equals. And when you see the formula for a confidence interval in the textbook, you'll often see it'll look something like this. It'll be x bar, which is the sample mean, plus or minus what we have here, which is the margin of error. All this formula is saying is that to get a confidence interval, you take the sample mean, the x bar, and you add and subtract the margin of error. Because this entire piece that comes after the plus or minus sign is the margin of error. This is the margin of error formula. And in the next part of the video, I'm going to show you how to actually use this formula to calculate a confidence interval when you're taking a sample from a big population instead of a small population like this one right here.